differential privacy. Thatchaphol is an assistant professor in the Computer Science and Engineering Division at the University of Michigan. He received his PhD in computer science from KTH Royal Institute of Technology in 2018, advised by Dhanapon Nanankai. Between 2018 to 2020, he was a research assistant professor at Toyota Technological Institute at Chicago. And he works on dynamic graph algorithms and has a broad interest in modern models of computation, including online, sublinear, parallel, and distributed.
Thanks a lot. Okay. So today I will talk about how to deal with adaptive adversary using differential privacy. And this is a joint work with a lot of amazing people who know much more on differential privacy than me. So one of them is Haim here. Okay, so but I just get kind of excited about this connection, and basically, although I'm not the expert, I want to share it with you. Okay, so first of all, in this talk there will be two types of adversary that we consider. One is oblivious adversary. This is so first of all, adversary is just a guy who generate updates to our data structure. And oblivious adversary is such that it will fix the whole update sequence from the beginning and review the update sequence to you to the data structure one by one. So everything is fixed from the beginning. So that's why it's called oblivious. It doesn't depend on what data structure return. Another one is adaptive adversary. This is the adversary such that the next update is generated based on previous answer of the algorithm. So this one is stronger than this one. We want to get the data structure that works against adaptive adversary in many settings. For example, when we want to use it as a subroutine inside static algorithm. And for this talk, I will use this word for short, like the algorithm is robust if it works against adaptive adversary. Otherwise, if it only works against oblivious adversary, I said that it's non-robust. Okay. And yeah, what we're gonna see is a black box transformation from any non-robust algorithm to the robust one for estimation problem. So it's a problem when you want to maintain, let's say, one number, okay, using differential privacy. Okay. And the goal is that, like basically, you will see two cool property from differential privacy that I think is good to know, even if you care about data structure only. And another is like you see how they like combine, how this property combine together and give us this black box transformation. Okay, so this is based on the joint work with many people, including Haim. Okay, so let's see the reduction. It's going to be simple, but before we go to the real reduction, let's talk about the setting. Just set up some notation. So let's say that X is your input that undergoes an update, okay? And so like Xi, we use it to denote the input at the ith step, at the ith time. So it's just an initial input X0 after applying ith many updates. Okay? U1, U2, UT, U3 until UI is just an update that you give to the input. Like you can think of this as an initial graph, and this is an edge update to the graph, for example. And I will use X vector I to denote the sequence, the update sequence from the beginning up to time I. Okay. So what's really happening is like you have adversary at time I, it gives us the ith update, and you have algorithm A, which output what it answers based on the update sequence it's seen so far. Just a simple setting. And now we will consider dynamic algorithm for estimation problems. So what do I mean by this exactly? So when you have x as an input, that under like dynamic input, let's say that g of x is just some function depending on the input. Can be size of the minimum cut, st distance, anything, just some function. Okay. So algorithm, we say algorithm maintain a gamma approximation of g of x if for every step I, well, the algorithm, given the update sequence up to time I, return something that is within like a gamma factor of g of xi. Right, so that's the setting. And now let's see one very simple black box transformation. Yes?
I would imagine this is in a probabilistic setting. So do you need probability somewhere?
Good. So I want this thing to hold for every step I, let's say with probability at least 0.9 for every step. No, for all steps, actually.
Yeah.
Okay. So let's see at least one simple black box transformation. Okay, suppose that you have a non-robust algorithm A, such that it maintains gamma approximation of some function. And this is correct throughout the whole sequence of t updates with probability 0.9. And let's say that it can handle this sequence of t many updates using t total update time. Well, how to get a robust one? There is, like, you'll see it soon, but like, we can get like a robust algorithm A prime, right? That maintain our gamma approximation with the same probability, such that the total time to handle t update is t total times t. Okay. And let's see so basically there is like a blow up of t here in the total update time. Okay, let's see how to do this. We just kind of do something almost trivial. That is, we initialize t many copies of non-robust algorithm A1 up to AT. And for each step I, just feed the update UI to every copy of A, and then return the answer of AI at step I. So why this is robust? This is because, well, we use the randomness of AI is leaked only at step I, but once we use once this information is leaked to adversary, we'll never use AI again. But you see that okay, this works, but the total update time is blown up by a factor of t. So now let's see how to get something a bit better. Suppose we are in the same setting. You have a non-robust algorithm, okay, such that it handle t update into t total time. What we're gonna see today is that we can get a robust algorithm A prime that maintain gamma times 1 plus alpha, just a bit worse approximation, with probability it can be even better. Doesn't matter too much here. And it can handle t many updates using t total times root t, total update time. Yes?
Just a question. So you mentioned that the adaptive adversaries only sees the previous outputs, but doesn't see the randomness of the output. Does it make a difference?
It makes a lot of difference. So the question is whether this is it important to say that the adaptive adversary see only previous answer and not the random choice inside the algorithm? And the answer is yes. We only assume that it only sees the answer, and this is crucial for this technique to work.
Yeah, I mean, just going on that, doesn't that reduce the applicability. I get, yeah.
So yeah, this is still quite applicable because when you use data structure to interact with when you use data structure inside as a subroutine in the static algorithm, the way that the algorithm interact with data structure is usually just depends on the answer. It doesn't really try to see how you use the randomness inside. Okay, good question or good questions. All right, so you see we get this improvement of root T. Yeah. So this is just a simple to state thing. There will be a more advanced version of this whole thing, and it gives a bunch of application to dynamic graph algorithms. Previously, adaptive algorithm, robust algorithm are quite slow, and with these techniques, you get something that is non-trivial, although not as fast as the oblivious one. Anyway, this is what we want to look at today, the simple to state transformation. Okay, so let's see the description of this transformation. It is quite simple too. Okay, so what we're gonna do is instead of having T many copies, just create square root T many copies of non-robust algorithm, A1 up to AC, when C is around root T. And at the I step, okay, we do the same thing. We feed the ith update to every copy of A. And after that, what we're gonna do, we return the median of all the answers we have seen after round it up by power of 1 plus alpha. So you just look at what each copies of A return, round up a bit, and then return the median. This is almost the whole thing. Except that the correct, the precise description is just that instead of median, I changed this to something called private median. Okay. That's it. That's the description. And I will not actually describe how exactly it's simple how to do this thing, but I will just talk first what does it mean to be private here.
What, are you going to say where you need to round?
I just want to round so that okay. The question is why we need to round. The answer is we want to round just so that the universe of numbers that we will ever see is finite. It's not you don't want to work with real numbers. You will see soon why we need this in the promise of from the property of private median. We need to work with finite universe. So that's the description. But now we want to see why what does it even mean here, private median? And yeah, this is gonna be about differential privacy. So let me tell you what it is. So let's say that you have a set S, which is a list of elements from universe X. We're gonna say that an algorithm is epsilon delta differential private or epsilon delta DP if for any input S and S prime differing on one entries. By differing on one entries here depends on your application. It can be this can be a table and it differ on one row. This too can be two graphs, differ by one edge or one node. Depends on your application and what you want to concern, what you concern. Okay. So given two input S and S prime differing on one entry, and if you look at any subset of outputs of possible output O, then you want that the probability that A given this input S and answer something in the set O is basically the same probability when you change the input from S to S prime. So we have multiplicative factor and additive factor here. The additive factor here, you should think of something like very small, 1 over poly n. This one, you can think of small constant. Okay. In other words, the output of A is stable under change of the input. So privacy is just stability of the algorithm. So you want this thing to be like smaller. The smaller, the better. The smaller, the more stable you get. Okay. And private median is the algorithm that do this. Okay, you have a list of elements from like totally ordered universe. And the subroutine private median is an algorithm that is differentially private. Something like 1 over S private. And it runs in time basically linear in the size of the input. And here you have log X. So that's why you don't want to work with real number. You want this thing to be like finite. And what it does is just it returns like some element in the universe. This element X might not be from your set, by the way, okay? But the rank of X with respect to your set should be something close to median, close to half. So it's really just median, approximate median, but it's private. Okay. So you just think from now that if you have a set of size S, you can return a median of it such that the privacy is something like 1 over S. Okay. So now that's kind of explain. I just explained the input output of private median, and that basically completes the whole description. And you see that the total time that we need to spend is T total times square root T. Because we really just run root T many copies of A. Yeah. Yes.
Can you just say one word about what specific Laplace distribution you're sampling over if it's kind of an unstructured set?
You mean go inside this thing, right?
Yeah, I mean, you have it as a comment, assume you can sample.
Right.
I was just wondering what Laplace distribution it is.
Can we take this offline?
Sure.
I mean, it's simple, but I just kind of want to skip this for a bit.
Sure.
Yeah, thanks. Yes.
So I'm wondering, what if you don't feed the update UI to every copy, you sample just few copies, and then maybe you can somehow exploit batch dynamic algorithms. So that, if
Yes, good question. So the question is, can we, instead of feed everything to every copies and just subsample these copies and just, so I will get to that soon. It's definitely the way to speed up this framework. Yeah, it works. Yeah. Okay. So the rest of this talk, I will just now show you at least how things fit together, and why A is now should be still accurate, even against adaptive adversary. Yeah. All right. So So the main step is this. The first step I will try to convince you is that the random string, the random choice that we feed to each copy, AJ, are private. And this is really the most important insight of this technique. Actually, the privacy is to protect the random string. It's not to protect, like, it's not on the answer of A. No, it's not on the input of A. It's on the random string of A. Sorry, this should be input. Once you get that your random string is private, then we can show that most of the copies are accurate. And once you know that most of the copy are accurate, then because you return the median of this answer you return the median of these copies, then your A prime must be accurate. And for each step, like I will tell you how we apply differential privacy properties, which is one is adaptive decomposition, another is generalization. These are the two cool things that I think it's good to know.
Is the square root t tight for this?
I think for these techniques, this square root t is tight. Yeah.
And does it come from the tightness of the adaptive composition?
Yes, you will see. Yeah, right. This is tight because, I mean, you get this upper bound of square root t using adaptive composition. The lower bound there is a lower bound from adaptive data analysis that give the tightness of this technique. Yeah. All right. So I wanted to first tell you about this thing. Okay. So what is adaptive composition? Well, we said that A is a composition of A2 and A1 on input S. If it computes first, like A1 given the input, and then it output out one, and then A2 look at the input as well as the output of A1, and it output out2. Okay, so this is why it's adaptive. Like A2 also look at the output from A1 and give you output 2. Okay. And A just output both outputs here. This is then if A works like this, then like we said that A is adaptive composition of A2 and A1. And now, what's cool about differential privacy is that you get it preserves privacy under adaptive composition. So if you have k copies of this epsilon 0 DP algorithms, and you compose k many algorithm here adaptively, then one can analyze this, and like the first basic analysis show that A is k epsilon private. But with a better analysis, one can also show that actually, if you are willing to pay some additive error here, and this can be super small, then A actually is something like square root k private. Yes, like the loss in privacy here is just from epsilon, you would get loss of something like square root k. And with something here, but like this is going to be negligible because you get epsilon square here. So the reason why we have like this square root k here is going to be the reason why we get square root improvement. And epsilon here will be chosen such that this is negligible. And the very high level intuition why you get square root k instead of k at all is like kind of when you do k random walks in 1D, you should be like within root k instead of k from the original. So anyway, that's adaptive composition. Let's use it to show that your random string are private. So I will need some notation again. So let's say that I use rj to denote the random string used by the non-robust copy aj. And capital R is just this collection of rj's. And output at time I, out prime I of jar is just the output of A prime at step I. When this collection R is fed to these non-robust copies. So like given the ith at the ith time here, right? Given the ith update, this algorithm A prime return the private median of these copies J when this is the input of like update sequence so far. And this guy depends on this random string Rj. And you return this private median. And this is just the output at time I. So the transcript between algorithm A prime and adversary is just this tuple, like this update and output. And the transcript of the whole thing is just, you get like initial input and the transcript at every time step. Okay. So what I'm gonna do next is just to show you that this whole transcript is private with respect to R. So like this transcript is stable, right? When you change like some like when one of the like when you change one random string in this collection R, this whole transcript is stable. So meaning that this transcript doesn't reveal this information about the random string. So why is this? Well, first of all, if you fix any I, okay, the transcript at time I is just like update and this output at time I. I claim that this is gonna be something like 1/C private. The reason is just this output at time I is just a private median of C many numbers. And so this thing is going to be 1/C private. And then the transcript at time I is just like, it's just a post-processing of this thing. It's just a function depending on out I prime of R. So the transcript at time I is something like 1/C private. So 1/√T private. But then once you look at the transcript over all time step, this is just the adaptive composition of Ti over all T. And then you do the advanced decomposition. And then you get like your privacy will get worse by a factor of √T because this is the adaptive composition of T many things. Get worse by √T. And then you choose C here, right? To be C here is big enough so it cancels with √T. Then you choose C. You choose C to be like something like big enough, like close, like √T times polylog, say. And then this is like a small constant now. Okay. All right. Hope that this makes sense.
What were the two parts again?
So again.
Go back one slide.
Yep.
Oh, with you had the DP elements. One was adaptive composition, and the other one was
Basic. Here.
no.
Generalization.
Generalization.
Oh yeah. I didn't talk about that yet. Yeah.
Okay.
Yeah. Okay. So this is just the first step. So far we have that this transcript is private. Okay. Now we're gonna use the fact that this transcript is private with respect to this random string to claim that actually each copies AJ here actually will return something quite accurate at each time. This will use generalization of DP. And okay, let me tell you what it is. So to talk about it, I need to start with like some warm up, which is, let's say that D is some distribution over some domain X. And let's say I fix some predicate H, okay? Predicate that map X to 0 or 1. If you want to estimate the expectation of this thing, like how many, what's the fraction of X from this distribution that give 1 to H. Okay. That's easy. Well, you can just sample like something like 1 over epsilon square independent elements from D and just average. And then by Chernoff, you get this concentration, and this is all good. So this is when this is true, like when the empirical average gives you the real expectation, then if we say that this samples S generalized to D, to this distribution. However, this clearly completely failed if H here, if you can choose H here, depending on the sample set. H is if H is adaptive, because H can totally overfit the sample set. Like you can choose some H such that like for everything in your sample it gives 1, for example. But now next slide you see that actually if H here is chosen by private algorithm, then you still get generalization even if H is chosen adaptively. So that let's see what I mean exactly. So and conceptually, this is like the most important property, at least to me, of DP. Okay. So you have the same distribution D here. Let's say you have this S, like S is just a sample, T independent sample from the distribution D. And now, okay, suppose that you have an algorithm that, given a sample, it chooses this predicate H depending on the sample. Okay, so H actually depends on S. Now the point is that if this algorithm actually is private, it turns out that this empirical average here is going to be the same, with, like similar to the expectation with some error. So this is really cool to me. And like, what does it say? It says that generalization is guaranteed as long as H is chosen by private algorithm. Even H is adaptive, doesn't matter. If it is chosen by private algorithm, you get generalization. And this makes sense because the output of private algorithm are stable enough, right? Such that like this guy H cannot manage to overfit the sample. But we would take this okay, we'll just believe this, yeah. And we'll see how to use it.
Actually, just a stupid question. So if H depends on the sample, how do you define the first expectation? Because it should depend on the whole sequence. Like the expectation in green only has 1 sample.
Oh.
Right, and somehow H is supposed to depend on T samples. I'm just,
So H is a function of one element in X, right? So here you just sample X independently from everything and look at the what is this value and look at the expectation. Here you just look at the empirical average of Hx from your sample. So,
right, okay, so first take the empirical sample, then choose H, then evaluate it on expectation against the entire distribution that's the left.
yes.
So even the number on the left kind of depends on the sample because H depends on the sample.
Yeah, the number on the left here depends on can depends on S because H depends on S.
Okay.
Yeah. Good. So this is important slide, and it's good to know this one, even though you don't care about the rest of the talk. So yeah.
There's no dependence on S in the error, like the size of S.
There is no dependence on S on what again?
In the error bound, there's no like size of S.
No, there is no size of S. No, there's no dependency on S here. All right. Okay, let's see how to use this generalization of privacy. Okay. Yes. So last notation is this thing. I said that accuracy given R when the input is xi is just an indicator whether like A given this random string and the sequence update sequence xi like is accurate, whether this is accurate, like that it return this gamma approximation. And okay, so I said that this U is like a distribution, uniform distribution, and R here just again the collection of random string that we feed to each sample, that we feed to each copies of the non-robust algorithm. So just from this notation, you have that this accuracy of Rj for the sequence up to I, the update sequence up to I. This one is 1 exactly if Aj is accurate at time I. That's the notation. And now let me ask you this: like I claim that this thing accurate of xi for R star when you sample R star from uniformly independent of everything, this must be at least 0.9. So why is that? When R star is just random string independent from the input sequence, this accuracy must be high. Well, the reason is just this. This is because this is precisely the guarantee of non-robust algorithm, right? So non-robust algorithm, when your like random string is independent from the input, you get a good guarantee.
This is sort of one I.
One I for each I. Yeah, for one I. Yeah. Okay. Last technical slide. So last two actually. Sorry. So okay, you have this collection of R here. Okay, and you have this definition. Now I claim that this thing that looks like expectation and this thing that looks like empirical average is close to each other. And why are we done with if we have this? Because I will prove this claim in the next slide. Why? But given this, why are we done? Because we know that this thing is big, is close to 0.9, is at least 0.9. So this thing is like big, like 0.89. because they are close to each other here. What does it mean here? It means that most of AJ is accurate at time I. Like AJ is accurate at time I for most I, because this is just two. This is one if AJ is accurate at time I. So most of it is accurate. And if you return a median of this of the answer from AJ, you would be correct. So now I just need to show you why this expectation and empirical average is close to each other. Well, we of course use generalization, and what we're gonna do is to view this transcript as an algorithm that given the collection R and output this predicate. Okay. So like when you fix this collection of random string R, feed it, like when you fix this, then the transcript will determine what is the input so far, like the update sequence up to time I, which determine whether like this function that depends on xi, like the update sequence up to xi. So it means what? It means that this thing, like we know before that this transcript is private with respect to R. So it's a private algorithm. And so like this thing is like a predicate chosen by private algorithm. And so by generalization of the privacy, you get that this is this predicate that is chosen by private algorithm must be close, like this empirical average must be close to expectation. Okay. Yeah.
So just going back to Akshay had a question about how big C has to be. Like, you don't have the same thing that C should be at least some, 1/epsilon square size. Like the
well, C here I chose it to be even like root T. So
right, okay, yeah. So but there is something about C needing to be big.
It need to be quite big, yeah. All right, I'm kind of out of time. So so you see that most AJ are accurate, and so A prime is accurate. Okay, so let me conclude. We get this like transformation such that you get this factor of root T, and there are some extension you can get speed up using subclamping that Chais mentioned, and you can speed up using another technique. But let me conclude with a quick open problem. So far, this transformation works for estimation problem. It would be cool to have some black box transformation for search problem, like maximal matching, maximal independent set, anything. Yeah. This is some concrete problem that I would love to see robust algorithm. And if there are more conditional rule about, that would be cool. Yeah. Thanks a lot.
Thanks, everyone. Great talk. We have about 2 minutes for questions.
So
Yes.
one of the issues with search problems is there's too much information in the answer.
Yes. Yeah, we review a lot of information. So yeah, it's not clear how to do it.
Thanks.
Do you think this root T is a bottleneck for a differential privacy-based approach?
I think so. I think at least like in the streaming setting where like Time and other people did before, like there is some tight bound for this approach.
For root T?
Yeah.
Okay.
So if I only care about if there's a very big matching or very small matching, I only want to distinguish these two cases. Namely, I want to know if my output is larger than 0.99 or less than 0.1. Is root T tight? Can we beat root T?
I am not sure. Like this technique doesn't give that improvement directly. Like I don't see how to exploit that. Yeah.
I see.
Yeah.
I'm a bit I thought you said the root T bound can be improved with subsampling.
Oh no, I mean, so good. It can be improved, like the number of copies. I don't see how to improve this, but the implementation of this whole thing can be speed up instead of giving updates to root T many copies at each time step. You just sample, log in among these copies, and feed the update to those guys. So like,
so the overall update time would be,
yeah, the update
better.
time, like from the perspective of the each non-robust algorithm, like it will sample only root T times throughout the whole sequence of T update instead of T times. T steps. Good question. Like, yeah, this thing I don't see how to improve, but there are ways to improve the implementation.
I'll ask one last question. So your guarantee was at each time step you have a 0.9. You're like on average you'll like succeed in like 0.9, 90% percent of the queries. Is there an easy way to boost this with high probability?
So all of this thing that we said, like this probability can be boosted to high probability easily.
Okay.
Just make copies. Yeah.
Okay. So that wouldn't mess up with the differential privacy.
No.
Okay.
No.
Thanks. Thanks again, Thatchaphol.
Thank you.
Yeah, we'll have a 30-minute coffee